Another consequence of the constant speed of light that we need to deal with is that of length contraction. In the dot points there you can see I've highlighted the relevant sections that relate to length contraction. We'll have a look through this video what length contraction is, and we'll tie it back into time dilation. But before we do that, we're going to just reiterate that point that both observers in different inertial reference frames will actually agree on their velocity. So we need to start there as a key point, and that will help us to then link time dilation with that speed. And the agreement there is simply because they're making a measurement of the other's frame of reference as it moves relative to their own, and so we get that constant relative speed as measured by the two observers. And of course they'll both measure the speed of light as being constant as well, so they'll both record 3 by 10 to the 8 meters per second as the speed of light from their inertial frame of reference, just as a reminder. They will both observe time passing differently though, as we saw with time dilation. So the speeds are the same, but the times that are involved are different. And that means that the distances that they then measure must also be different. So we can talk about the distances travelled by an object, or we could talk about the lengths of objects in those frames of reference, and as a result we get the consequence of length contraction. To make that a little bit more understandable, we'll go back to our Desmos representation again, and you may have noticed in the previous uses of that representation I've actually incorporated length contraction, but we'll talk about that more specifically now. So here we once again have Alice on the train and Bob observing from off the train. Given that there is no relative motion between the two, they're both effectively in the same inertial frame of reference, and so they both record the length of the train as being its proper length. Now we'll add in some pointers here to indicate that proper length as seen from Bob's frame of reference, and we'll start to make some comparisons to that length as Alice starts to move past Bob at relativistic speeds. So as Alice now travels past Bob at a fraction of the speed of light, we can see that the length of the train as observed by Bob appears shorter than its proper length. This length is known as its relativistic length, sometimes referred to as the contracted length as well. And we can see that that effect becomes much more prominent the faster that Alice moves, so the train becomes even shorter at faster speeds. Now, if we switch reference frames and travel along with Alice in her inertial reference frame, you'll notice that the train is now measured to be its proper length, but as Bob moves past, you can see that the sign that he's standing beside becomes length contracted. So the effect of length contraction is only observed for objects that are moving relative to the observer. Now, to define length contraction, and referring to the definition that's in the glossary of the syllabus, an observer that is at rest, so they are in an inertial frame of reference, and they are at rest relative to a moving object. And again, when we're talking about objects here, we're not necessarily just talking about the length of the object, we can also talk about distances. They would observe that moving object, and again we could think of it as a distance, as being shorter and by shorter we don't mean in height, we mean in length, and shorter in length along the dimension of motion. So you'll notice from that train representation that we saw, there was no change in the height of the train, there was only a change in the length of the train, and so the length of the train appears shorter in the direction that the train is moving. As with time dilation, there are two key terms to be aware of here. I mentioned those in the Desmos representation. They match up somewhat with the concepts in time dilation. The first one is the proper length, and we'll use capital L with a subscript 0, and that's the length measured, and again this is the definition from the syllabus, it's the length measured in the frame of reference in which that object, or again that distance, is stationary. or is at rest. So anytime we use that subscript 0, that's looking at the object at rest or when it's stationary. The other term then is the relativistic length, and as I said, it also sometimes is referred to as the contracted length, and we use the symbol L with no subscript. And fairly similar definition apart from the last few words. Again, it's the length measured in the frame of reference in which the object is in motion. So there's the two key terms, and we'll relate those back to an equation and also tie them back into time dilation as well. To develop that equation, we're going to have a look at the scenario that we considered for the twins paradox. So we're going to consider Alice travelling to a distant star. So we're not going to worry about the return journey, we're just going to have a look at her trip to a distant star and the times and lengths that are involved in that scenario. And to start with, we'll consider Bob's frame of reference. So we'll use that same diagram again, and we'll add in the distant star to which Alice is travelling. Now, considering this scenario, we're looking at it from Bob's frame of reference, so we know that Bob's clock is going to record the relativistic time, and Alice's clock will record the proper time. But considering we're looking at Bob's frame of reference, we'll just deal with the time t. The distance that Bob's going to record is the distance from Earth to the star, and considering it's a distant star, that distance is close enough to being constant, and it's measured from Bob's frame of reference, so he's going to record the proper length L0. That means that when we consider the velocity with which Alice is travelling, we can identify from Bob's frame of reference that v is going to be equal to the distance L0 over the time t. If we now move across to Alice's frame of reference, you'll notice that there are a few things that appear different from her frame of reference, and if you go back and look at the previous video, you'll notice that the diagram is actually incorrect because it doesn't incorporate the length contraction effects. So if we include that diagram here, the key differences that you can observe are the fact that Alice's rocket now actually looks longer in her frame of reference, because Bob would have recorded the relativistic length of her rocket, and notice also that the distance between Earth and the star is now shorter because Alice is recording the relativistic distance between those two. So this length from Bob to the star, as recorded by Alice, is going to be the length L, but the time that Alice records is going to be the time t0 because she's stationary with respect to her clock. So the velocity of the Earth as it moves away from her and the velocity of the star as it moves towards her would be given by v, which is equal to L over t0. Now you'll notice that we have two expressions for the speed v. We'll equate those together and then apply some algebraic steps to identify what the relationship between L and L0 is. So just listing those out again, we had v was equal to L on t0, which is also equal to L0 over t. Now rearranging those, we can write that L is equal to L0 multiplied by t0 over t. So I'm just going to leave that term separate out to the right hand side because we can use the time dilation equation, so t being equal to t0 over the square root of 1 minus v squared on c squared, to rearrange that to get that t0 over t is simply equal to the square root of 1 minus v squared on c squared. So we're going to make that substitution for t0 over t, and we can then see that L would be equal to L0 multiplied by 1 minus v squared on c squared. So that's the equation for length contraction. So you can see that same term of the square root of 1 minus v squared on c squared appears, but in this case you'll always have that L will be less than L0. It's important to notice here too that the L0 and the T0 don't necessarily refer to the same frame of reference. So you can see that L0 is the distance from Earth to the star, measured from Bob's frame of reference, but t naught was the time that Alice recorded. So the noughts there don't match up. Just be aware of that when you're looking at these scenarios if you have to calculate both time dilation and length contraction effects. Now, looking at evidence for length contraction, given that we haven't managed to move any man-made objects at near the speed of light, we can't actually make these direct observations of length contraction. We can, however, use other experiments and the evidence from those experiments to confirm length contraction indirectly. We've already seen one specific scenario where that applies, and we'll talk about that in a second, but there is another one that we'll mention here as well. That first one is again about muon decay in the atmosphere. Now, just to reiterate that again, muons are being produced in the upper atmosphere, moving at very close to the speed of light, can be observed on Earth. Interestingly, if you go through and do the calculations, even when moving at near the speed of light, if you calculate how far they should be able to travel, those muons should not be able to reach the surface of Earth. But they are definitely observed reaching the surface of the Earth, and so that observation is valid. We do see them from the surface of the Earth, and so that can be explained from Earth's frame of reference due to time dilation. Now, since they are detected at Earth's surface, that means then that we need to consider length contraction from the muon's frame of reference. And the reason why that's important to consider is that in the muon's frame of reference, they would be recording the proper time, they being the muon, and so the distance that is travelled would have to be shorter in order for the muons to actually arrive on Earth's surface. So that distance as measured by the muons would be shorter. The second example that identifies evidence for length contraction is heavy ion collisions. So ions that are large in size, and those collisions that occur in particle smashes where they're occurring at near light speed. And the reason why that one's useful to refer to is that when you consider an ion, when it's stationary or while it's at rest, it would be spherical in shape. However, when they are undergoing collisions at near light speed, the evidence that has been collected there would suggest that the shape isn't actually spherical, and instead matches up with the shape of the large ions as being more sort of like a flat disk. When they're moving near the speed of light. So instead of being spherical in shape when their relative velocity is 0, when they're moving at a speed that is just below the speed of light, they end up looking like a flat disk as they're moving in that direction of motion. And that's due to this sphere being sort of squished inwards, or the length contracting in the direction of motion that the heavy ion is moving. So that's the details for length contraction. As you might expect, there is another paradox that we need to deal with length contraction, and we'll look at that in the next video.